So, dear colleagues, it's for me a big pleasure to introduce you on behalf of the Division of Mathematics, the winner of the fields, the former Pascal medalist, who is Felix Otto. In fact, he had an extremely good relation with a real field medalist. As you will see in a minute, he obtained one of the fundamental results that made Cédric Villani a winner of the Fields medalist. Anyway, so let's move forward. So Felix Otto has invented methods which had an exceptional impact in the mathematics community. His name is already attached to concepts as the Jordan Kinderlehrer Otto scheme, JKO as it is known. This is something in numerical analysis. Then he's very well known also for the gradient flow structure, finding the gradient flow structure of the porous medium equation. This is now partial differential equations. Then he's very famous for the Otto-Villani inequality, and now we are dealing, among other things, with functional analysis. He is also known for the Kohn-Miller-Otto theory of thin film in micromagnetism. And finally, I would like to mention the Gloria-Otto error estimates in stochastic homogenization. Altogether, Felix has written 120 papers which cover a remarkably wide area of subjects that I have tried to emphasize. I guess that it was always in science very difficult to be successful in different areas, but nowadays I would say it's even more complicated, and he succeeded in mathematical modeling, in analysis of partial differential equations, functional analysis, homogenization, geometry, probability. In all these domains, his contributions have been extremely fruitful, and also he has attracted a number of brilliant young researchers and has the most distinguished analysts among his collaborators. In fact, as a sign of his recognition, he is, there is only one Max Planck Institute in Mathematics in the Science, and he is one of the directors. Finally, just a few comments about his CV. He got his PhD with Luke House at the University of Bonn. Then he worked for several years in the US as a postdoc, in particular in the Carnegie Mellon and Courant Institute at New York. He was also full professor in the University of California of Santa Barbara, which I had the pleasure to meet him, as I don't know if you know Santa Barbara, but if you want to meet somebody, it's a good place to meet. Then he moved back to Europe, and in particular to his home university at Bonn, where he was full professor. Finally, he became the director, as I said, of the Max Planck Institute, and he is also honorary professor of the University of Leipzig. Finally, let me finish that he is the member of the German Academy of Science Leopoldina and member of the Academic Senate. So, please, Felix.
Luis Vega, thank you for this very kind introduction. It's an honor to be here, and I feel very honored to receive the Blaise Pascal Medal. it's a pleasure to give a talk in front of you in this wonderful surrounding, but I must say I'm also particularly moved by the fact that in the previous presentation by Professor Elise Marzahn, work of my father was mentioned. So that's probably a rare coincidence that this happens at the same conference. So I would like to give you, and I'm aware that mathematics is not an easy subject for non-mathematicians, but I will nevertheless try to give you an idea of work. I started, so let's see whether this works. Can you see the red dot? I can see it here, but, okay, so perhaps since I have this, I can move a bit closer. So this is work I started almost 10 years ago together with Antoine Gloria, who is now back in Paris after a couple of years in Brussels. And of course, many other people are involved, but in a certain sense, he is the most important collaborator. Since we had this morning the session on ERC, he a couple of years ago got a starting grant, and so it's a pleasure to have worked with him. So my talk will be on not on this very general topic of randomness and partial differential equation, but perhaps on something more palpable, namely the effective behavior of random media, which in mathematics is called stochastic homogenization, and I will explain where the word comes from. And I will start with physics, and I start with another famous British, so not Faraday, but with another famous British scientist, physicist, who apparently, so Maxwell, who apparently, according to a very nice book on random media, for the first time treated a problem in effective behavior of random media. And of course, that's something not very important in this whole treatise on electromagnetism. I think it's somewhere on page of the order of 270. It's more or less an exercise which he gave to himself and which he solved very nicely. And it's related to the effective resistance of a composite material. So I think we all know the notion of resistivity. So this is perhaps a thought experiment. You have an infinite slab of a conductor. You impose a voltage difference between the two ends of this infinite slab. And then since this is a conductor, there's a current flowing, and the current density is constant in space because the conductor, or one's thinking of a completely homogeneous material. And of course, there is a proportionality between the current density and the voltage, also bringing in the size, the thickness of the slab. And this is described by the resistivity, or one of the resistivity of conductance. And now he was giving himself the following exercise. He was thinking of a composite material where you have kind of a matrix which is made of the original material, but then you have, let's say, spherical inclusions which are randomly placed in this slab, and that's now kind of the composite material. And of course, due to the breaking of translational symmetry, in this situation, the current density will be no longer constant. But still, it's kind of intuitive that there should be something like an average or an effective resistivity of this slab, provided at least that the thickness of the slab is much larger than the typical distance between the inclusions. And he was interested in getting a number, so he was interested in assimilating this composite material to a thought homogeneous material. So he was interested in finding the effective conductivity in this situation. And he was operating, in order to be able to do that, he was operating in a regime, in a dilute regime, when the distance between these particles, these inclusions, is much larger than their typical radius, in which case he derived an asymptotic formula for the effective conductivity, asymptotic in the small volume fraction, which you find here as phenomena 17. So that's apparently the first example of explicitly solving, or at least explicitly in an asymptotic way, of solving a problem of effective behavior of a composite material, or as we would say in mathematics, of homogenization, because you assimilate a homogeneous material to a heterogeneous one. And we call it stochastic homogenization because the heterogeneous material is described in a stochastic way because you, in a certain sense, lack the detailed knowledge, and you just, in a certain, are dealing with an ensemble of materials. So, but nowadays, of course, in kind of material science or in groundwater and reservoir simulations, one has to deal with situations where there's no small parameter around, and where therefore you don't have access to exact formulas, and you resort to numerical simulation to infer the effective. Of course, it's not. Sorry. So did you hear anything? Okay. I'm happy that it was not all vain. So of course, it's not necessary, so I have to try to use both of my hands. This is very faint. Now, and of course, from a mathematical point of view, it doesn't matter whether you're dealing with the physical phenomenon of conductivity or elasticity. For instance, you might be interested in the effective bulk moduli of a composite, here is kind of carbon inclusions in a polymer, or as mentioned, you might be interested in the effective permeability of a porous rock, and so this could be all kinds of physical properties. And so for these situations, you have to resort to numerical simulations, and the engineers, kind of the standard method is the method of the representative volume element, which was the motivation for us, understanding the method, understanding the errors made in this method. And that was, in a certain sense, somewhat new terrain, because this is a quantitative question, or we asked a quantitative question, whereas on the mathematical level, most of the theory was on the qualitative level. And that, I mean, the fact that in all these situations homogenization occurs is understood since many decades. So it was a theory which was developed quite independently in the East, in the former Soviet Union, in the school of Kozlov, and also in the West by Varadhan and Papanikolaou, and later on embedded in a much more elegant French-authored theory of homogenization. But the question we want to ask the questions we wanted to ask are more quantitative, and that's what I want to explain now a little bit, starting by explaining what this engineering, very intuitive engineering method is to infer the effective behavior of composite materials. So, but for this I have to now make a little bit of a mathematical abstraction, so I'm now leaving kind of a specific application, and have to tell you that on the level of mathematical description, a heterogeneous medium, now be it a conducting medium or an elastic medium, is kind of described by a space-dependent coefficient field. So that could be the effective conductivity, which in general is a tensor. That could be the heterogeneous conductivity, which is a tensor, or it could be the bulk moduli if you're interested in elasticity, and that tensor field can be quite general, besides being what we would call in mathematics uniformly elliptic, so positive definite and bounded as a tensor field. And that one gives rise to what we call in mathematics an elliptic operator, which I'm sure the physicists certainly will be familiar with. So for instance, think of U being an electric potential. So minus the gradient of U is the electric field. If you multiply it with the conductivity, you get the electric current. And then this gives you, if this quantity, the divergence of the current is equal to 0, you would be in a situation when there's no charge accumulation. So in a certain sense, the physics are all in this operator. And now the randomness comes in mostly because in practice a lack of knowledge. That means you don't know the details of this coefficient, of this heterogeneous coefficient field, but you have a probability distribution, or as physicists would say, an ensemble of such coefficient fields. So you're looking at a random elliptic operator and you want to understand the macroscopic behavior. And just to fix ideas, because that example is already interesting from a theoretical point of view, and the numerical simulations which I'm going to present are related to this example. Think of the following example. Think of a little bit like in Maxwell's case, but in a non-dilute situation. Think of the red points being randomly distributed in the plane or in space. So you would say they're distributed according to the Poisson point process, let's say with density normalized to 1. And consider balls of radius, so consider spheres or solid spheres of balls of radius 1/4 around these points. Consider the union of the set, so that's a random set. And now assume that on the union of the set, your conductivity has one value, let's say the higher one, and on the complement it has a lower value. That's a very simple example, which in a certain sense already contains all the, from a mathematical point of view, all the difficulties which would be there in more sophisticated examples. So, so what's the goal? The goal is to extract the effective behavior from these statistical specifications. So, so in a certain sense, you want to go from one simple object, which is the ensemble, and which here in this case is just characterized by 3 numbers: the density of points, which here was set equal to 1, the radius of the inclusion, which arbitrarily I set equal to 1/4, the conductivity in the pores. So 3 numbers. You want to go to another set of 4 numbers, but in fact it's just by symmetry, it's just a single number by isotropy of the effective behavior. So in a certain sense, you want to go from 3 numbers to 1 number. That looks extremely easy, or like a simple question, but there is no closed formula to go from here to here. So you have to resort, in order to infer this, you have to resort to numerical simulation. So, so what do the engineers do? They would sample this random medium, but they would not sample it of course they couldn't in the whole space, but they would kind of introduce a representative volume element, something which has a finite size, and the most non-intrusive way of doing that is to introduce kind of a periodic boundary conditions. So in mathematics we would say doing this on the torus, because you're identifying this boundary with this boundary and this boundary with this boundary. And of course also in this artificially periodized setting, you can look at the same statistics. You can look at the Poisson point process of density 1. You can do the same geometric construction. Of course, you have to kind of take care of the fact that something which is here also is there because of periodicity or image charges, if you want. So so they would sample this this artificially periodized medium, and then they would carry out D, if D is the dimension. So in this 2-dimensional picture, just 2 prototypical calculations where they would seek a periodic correction of the affine potential phi I in such a way that the corresponding current, so A times the gradient of the potential, is divergence free with periodic boundary conditions. And then they would consider the flux and would take the spatial average, so the average over this element of the flux, as a good approximation of the effective conductivity in the ith coordinate direction. So that's the basic idea of this method. And in order to make it a bit more palpable, let me show you numerical simulations. So just in 2D. So in 2D, you would just carry out two numerical simulations, one for each coordinate direction. So in the first case, you take the horizontal coordinate direction. So you would, what you do, you find a correction phi 1 to the affine potential in such a way that the flux is divergence free. And so, so as you would expect physically, in the good conducting region, the potential lines are further apart because the field essentially is more expelled than in the badly conducting region, and the current, of course, would try predominantly to flow through the well-conducting region. And then you would take this current field and average it over this period cell. You would get a vector, and that's the first column of your effective matrix. And you would do the same thing for the other coordinate direction, where, of course, now things change. The current is predominantly upwards, whereas here it was to the right. And that would give you an approximation to the second column of the conductivity matrix. So we were interested, so the question, I mean, what got us started working on this subject is we wanted to understand the error that's made in this method. So what nature is the error, and how can you kind of predict in a very general way how it behaves, and I will try to explain why this is of interest. So the first, in order to understand the type of error, and I think many of you will kind of see that instantly, it's important to realize that the answer you get from this method, of course, depends on the realization of your medium. I mean, your random number generator. So this would be one realization, potential flux, that would give you this matrix. This would be another realization. Of course, it would give you, I mean, everything looks different, so it would give you a different answer, where, of course, you notice that the two answers are not that far from each other, but it's a different answer, and a third realization would give you a third answer. So the answer you get is fluctuates. It's a random variable, so it depends on the underlying realization. So that's, of course, the first source of error, but it's also very intuitive that this type of error becomes smaller as you make your representative volume size larger. As you look at a larger system, of course, then you have to work more, or your computer has to work more, or you have to wait longer. And so instead of looking at a larger system because the problem has a scale invariance, or in order to fit it on the screen, you just look at you scale down the inclusion. And so here are three realizations for the small representative volume element. Here are three realizations for the larger ones. And you see while here the fluctuations are perhaps in the range of 10%, here they're closer to 2%. So it's clearly that as you make the system larger, there's more and more self-averaging happening, and therefore the error, this random part of the error, should go to 0. But that's not the only error. There's a second one, which is perhaps a little bit more subtle, and that has to do with the fact that by going to this periodized medium, you've altered the statistics. You've changed the rules. You're not looking at the same problem anymore, and that's where it becomes very apparent. If I repeat the cell periodically, that's in a certain sense the problem which you're solving, and then you realize that suddenly you've artificially introduced long-range correlations between the position of the particles. So whereas, of course, the Poisson point process has no correlations. It's kind of finite range process. So what's happening over there is completely independent of what's happening there. So that's so you've falsified the statistics, and that's seen in kind of in this numerical simulation. If you would look at the expected value of your, if you would have complete access, numerical access to the expected value of your fluctuating answer, then you would get an isotropic matrix just characterized by the single number. But this single number still depends on the size of the representative volume element. As you make it larger, it converges, or you hope that it converges to a fixed value. So that's the second type of error which arises in this method. So, and it's very clear, kind of, so here's kind of repeating the slide. So the strategy, the engineering strategy is you randomly pick a realization according to the periodized ensemble. You solve for these 2 or 3, depending on whether you're in the plane or in space. These 2 partial differential equations. You compute the spatial average of the current. You take this as an approximation. You're making 2 errors, and by Pythagoras, the squares of the error sum. One part of the error is the random error, the fact that your answer fluctuates, so the variance. And the other one is the systematic error, the somewhat more subtle error, which I mentioned last. And by the qualitative theory, since more than 40 years ago, we know that these 2 errors go to 0, as it's very intuitive, as you make the representative volume element larger. But so we were interested, and that's what I meant at the beginning, we were interested in quantifying this. So why should you be interested in quantifying this? Because it tells you something about what the best numerical strategy is if you don't want to spend too much time in computing this. Because when you set up, when you do this on numerically, you have 2 knobs to twist. Not only can you kind of decide on how large your representative volume element is, but you can also decide of how many samples you will be looking at. So you can have, in a certain sense, if what's at your discretion, if you want to just spend a certain amount of floating point operations, is you either can put all the unknowns into one big sample, or you can compute many moderate-sized samples. And that has a very different effect on the error, because it's kind of intuitive that by taking the empirical average, you dramatically reduce the random error, but yet that has no effect on the systematic error. So, so understanding how the random error and the systematic error behave with L gives you a way to answer what your optimal split is in the numerical strategy. So this is why it's relevant to do that. And so with Antoine Gloria and then later with Stefan Neukam, we found the clear and the optimal answer, which is that the random error, here's the square of the random error, is much larger than the systematic error. The random error, in a certain sense, scales as you would naively expect by a central limit theorem scaling. It's the square of the error scales like 1 over the volume of the representative cell, so D is the dimension, whereas the systematic error is much smaller. It's the square of the, up to a logarithm, the square of the random error. So it certainly pays a lot to look at many kind of samples instead of putting all your computational power into one big sample. How much time do I still have? Does anybody, unfortunately I didn't. If we want to stay on schedule. Okay, no problem. So, so of course, this is just a slide which is probably in the details of no interest for you. There people have tried or have answered this question to some extent already before, and there were works afterwards. So this is an active area where many people contributed. So let me finish by kind of just mentioning two other questions we addressed, because in a certain sense, by addressing this question, we developed the right tools to kind of address or answer further questions. And one of them has to do with the far field behavior in a random medium. So, so the question is, again, think of kind of conductivity and charge distributions. The question is it if you have a very localized charge distribution F that's neutral, and you're interested in the electrostatic field that's generated by this charge distribution in a random medium, so if you're solving this type of heterogeneous Poisson equation, is it possible to infer at least in an asymptotic way, is it possible to infer the far field behavior of the potential, or the field, far away from the location of the source, without knowing the medium in between? So, and indeed, this is the case to some extent. There is something like effective multipoles, but there is a limitation. In 3 space dimensions, you can infer, you can predict something like the effective dipole, the effective quadrupole, but not the effective octupole. And yes, it is true. I mean, it is possible to make this prediction without knowing the realization of the medium in between, but there is a certain limitation, and the limitation depends on the dimension. So sometimes in mathematics, it's a good idea to think of a general dimension, because that gives you more insight in the mechanisms, and in a certain sense, the higher the dimension is, the more of the further you can go in an effective multipole expansion. So that's one of the questions. And the other question is to kind of predict the, again, you're looking at a Poisson equation in a random medium. You have now a spread out charge distribution, and you're interested in macroscopic observables. Is it possible to, at least to leading order, to predict their fluctuations? So that's something like uncertainty quantification. Is that the case? And the short answer is, indeed, you can do that, and you can even do that without working much more than you would have anything to do in order to extract the effective behavior. So, so the leading order fluctuations, if you want to quantify, at least to leading order, the uncertainty in macroscopic observables is at computational hand, and you don't have to do any more work than the work that's required to extract the effective behavior, so the A bar. Okay, so I think that's all I wanted to say. So this was just a short glimpse, probably very impressionistic, of what Antoine Gloria and I, with many collaborators, started in the area of understanding in a more quantitative way the engineering methods in random media, so doing quantitative stochastic homogenization.